Hello everyone, I'm Shajib Ghosh. I'm going to present on my final project presentation for course EEL6825 Pattern Recognition Intelligence Systems. The title of the project is an end-to-end system for detecting and recognizing text in natural scene images using deep convolutional neural networks. So let's dig deep into my whole method and outlines. So the project outline includes introduction sections where I'll be introducing the problem and recent buzz about using deep learning in case of text detection and recognition. Also, I'll talk about the problem statement and the possible solutions to the problem. In section 3, I will talk about the existing approaches in case of text detection and recognition, as well as the developing end-to-end systems. Next, I will talk about the methodology I have adopted for developing the end-to-end system for text recognition in natural scene images. Then I will evaluate the performance and compare between two frameworks I have adopted for the system. Finally, I will conclude by summarizing the insights I have found from conducting the experiments. Also, I will discuss about the future research direction in case of syntax recognition and detection. So with the advancement of deep learning based solutions, syntax detection and recognition is becoming crucial in many applications, which includes content based image searchings, also robotic navigation, for industrial automation. It is crucial to have include automation in level detection or levels tagging and maintaining all these things in industries. Also for autonomous vehicles to control the navigation system automatically, syntax recognition will play a vital role. At the same time, for automatic identity authentication, syntax recognition is widely used. And finally, for automatic translation and summarization, for example, Google Translate, also text to speech conversion from images. Those applications are actually useful. Those syntax recognition is useful in these computer vision based applications. So the problem is, however, there are many deep learning based solutions currently are there for syntax recognition, but it is challenging compared to the scan based or document based optical character recognition system. The reasons behind that is, in case of scan based OCR system, usually the background is simple and clean, but for STR system the backgrounds are often complex. And if we consider about the appearance, then mostly the document based or scan based OCR system have a single color background with irregular font and size, and with uniform orientation and arrangement. But in syntax recognition, in natural scene images, we can see text of multiple colors with irregular font sizes and types, and also with diverse orientations and arrangement. Also, mostly scan-based OCR image. For scan-based OCRs, the document images are mostly clear and frontal, but for syntax recognition, many images and the text are actually distorted by non-uniform illumination and low resolution and motion blurs. Mostly scan-based documents images are actually acquired. When acquired, the parts are actually uniformly acquired, and for syntax recognition the texts are actually captured randomly. So all these things actually create problems for recognizing text from the natural scene images. So that's why there could be different solutions, possible solutions to this method. First of all, we need to develop an end-to-end system which actually incorporates detection and recognition phases with suitable backbones or CNN architecture. And also we need to use such benchmark dataset which include different type of font sizes orientations and diverse backgrounds and all different challenging case scenarios, so that actually the model learns well about different cases, so that that can tackle those challenging scenarios. Also, it is always a better idea to find appropriate combination of two-stage or a single-stage pipeline for the end-to-end system that actually takes the challenging cases into account. Finally, it's always a trade-off between the speed and performances. It may seem that in some cases, some detection algorithms are so robust that it take detection and recognition algorithms are so robust that it take uh, much more time than for inference. Um, Also require high computational facilities like GPUs. So optimize, but we can get better accuracy, but at the same time it will take much time and high computational complexity. So optimizing between this time and speed is very much important while developing an end-to-end system. So existing approaches. Earlier, there are different conventional machine learning based approaches like maximally stable extremal regions and stroke weight transform and tesseract OCR. But now, with the advancement of deep learning based approaches, there are many detection algorithms as well as recognition algorithms. For example, for detection, text boxes plus plus, craft, yeast, different segmentation and regression based methods, and a hybrid of these two methods are used. For recognition, mostly CTC-based method and attention-based methods are widely used. And for training this algorithm, ICDR dataset, syntax dataset, COCO-text dataset, total text dataset, this type of benchmark dataset are widely used. So the idea is to actually detect the text with the bounding box area regions with the inscribed text is the ultimate goal of syntax recognition and detection. So for this actually I have developed a workflow which have four major steps. First steps include actually syntax data, appropriate syntax data collection for training the model. Step B includes image pre-processing so that it can help the feature extraction method. Step C include text detection and localization, and the step D is the combination of three different parts. One is text segmentation from the detected text, then script identification for different languages, and then finally text recognition. So all these actually help the all these actually constitute the end-to-end system. So the dataset that I have used for this experiment or the whole this project are Synth 90K dataset, MLT dataset, ICDA 2015 dataset for inference, COCO-text and total text dataset. So four datasets for training and one for inference, mostly the test set of ICDA 2015 for inference. So I have used a combination of different language and different type of text images so that the model learns well. Actually, I have used a pre-trained model um, and a pre-trained model for easy OCR and parallel OCR framework. So I have used or adapted two end-to-end framework. One is first one is easy OCR framework and second one is parallel OCR framework for developing this end-to-end system. Actually, I compared these two branches of the system and decided that which one will perform better and which direction to go while developing an end-to-end system. So the first end-to-end framework actually take in images as input, do some pre-processing and use craft algorithm for text detection. After some mid-processing, it uses the text recognition pipeline, which is actually a CRNN or convolutional recurrent neural network. For feature extraction, it uses ResNet as a backbone. Then for sequence labeling, it uses long short-term memory, and for decoding, it is CTC. After some post-processing, the texts are recognized with bounding boxes around it. For end-to-end framework, all the backbones were MobileNet version 3, which is very lightweight. For this reason, for the inference time was much lower in end-to-end framework 2 than the end-to-end framework 1. So For the text detection, it used differentiable bandation technique with MobileNet version 3 backbone. The key features are it has a light backbone, it has a light head, it removed the squeeze and excitation block, it uses cosine learning rate decay, learning rate warm up, and filter pruning via geometric median. For after that, the DTT boxes are rectified using detection classifier with MobileNet version 3 backbone. It uses data augmentation, input resolution, and parameterized clipping activation for quantization. Also, it uses light backbone, as I said about the MobileNet version 3. For text recognition, CRNN was used, which has all the features of the text detection module, like it used light backbone, light head, feature map resolution, cosine learning rate decay, learning rate warm up, all these features, so that the whole system is very fast, at the same time gives decent accuracy. So the output result will be recognized test with the bounding boxes. At the same time, it also gives recognition confidence score. So now the evaluation metric that I have used for this one is like character level evaluation, because character is the key of a word. Most of the methods, conventional methods, actually doesn't give a better idea or the fair evaluation of the different methods. So it gives precision recall and h-min as measures. So the key features are CA level actually handles different split and merge detection cases, which is absent in the present state of the art methods. The scoring process actually conducts character level evaluation, then word level evaluation. Also, it provides very fine-grained evaluation of the end-to-end results. So these are the performances I have found after conducting experiment using end-to-end framework 1. It is a single image results. It can be seen that the words are detected, but they are not smooth bounding boxes around it. Also, the inference time was 8.8 second, and the recognition confidence was fair. Not so, for some cases it gave very good accuracy, good recognition score. For some cases it didn't do very much well. But for the framework 2, it gives a very good bounding box around the text instances with a very high confidence score for all the instances. Also, the inference time for this method was much less than the previous one. So it can be concluded from one single reference, but again, we'll evaluate the whole performance based on the ICDR 2015 dataset, which had 500 image data. So we can see that in case of detection, the craft algorithm for end-to-end framework 1 performed really well compared to end-to-end framework 2. In case of recall and h-min, but the differentiable bandation technique actually gave higher precision than the craft algorithm. Both the frameworks actually use CRNN algorithm for text recognition, and the overall recognition score was higher in end-to-end framework 2. For end-to-end precision, end-to-end framework 2 actually performed better. Also, if we talk about the speed, then end-to-end framework 2 only took 8 minutes for the whole inference of ICDR 2015 dataset, but end-to-end framework 1 took more than 1 hour for the whole inference. So the key findings include that end-to-end framework 2 has better performance than end-to-end framework 1 in terms of both speed and accuracy. Also, though the detection performance was good, but end-to-end performance still needs to be improved. Yeah, it is viable because if we talk about the speed, trade-off between speed and accuracy, most of the other existing methods actually take longer time for inference and require GPU for the performance. But the whole methods, the whole system was deployed for this project in CPU. Also, it can be there are mobile versions of end-to-end framework too. So it can be said that if we want to develop a very ease of use and user-friendly and light version of the end-to-end system, then end-to-end framework 2 is a better option. So to summarize, in case of in case of training the craft algorithm, weekly supervised training with the synthetic data was used, and that increases the model performance. If we use more fine tuning with diverse type of data set, then the model will learn better and it will give better performance. And it has been seen that the lightweight CNN architecture should be used as backbone of the STR system to make it scalable to deploy in mobiles and CPU without the requirement of GPU. So the system that I have developed using two frameworks and compare between these two, actually the system is faster, ease of use, and there is no requirements of GPU for inference. And but the limitation was there is a performance speed trade-off, and it can actually detect one language at a time currently. So my future work actually include using different attention-based recognition instead of city-space recognition to see that how well it perform and how I can develop a single stage pipeline instead of two stage pipeline for the end-to-end system. So we'll work on more about the performance and on the language barrier. But overall, the system is very easy to use. And that can be actually shown in the next part of the video, which shows the full demonstration of the methods I have developed. Thank you.